A graphene spray gun is a kinetic spray system that deposits, through supersonic acceleration, a one-atom thick sheet of pure carbon named graphene by means of a de Laval nozzle, a pinched tube with an hourglass-type shape. The system deposits graphene flakes and a hexagonal graphene lattice is created upon impact of the desired surface. The graphene spray gun would be utilized onto large-scale applications such as circuits, radio transmitters, and optical electronics due to the grapehene's transparency and its remarkable conductivity of electricity. The supersonic spray system was first developed in May 2014 by University of Illinois professor Alexander Yarin and Korea University professor Sam Yoon. Yarin went to Yoon when he learned about his work regarding kinetic spray deposition systems. Yarin believed that graphene could be applied to the system in order to create a layer of the material. After conducting experiments with the newly created system, they concluded that the graphene spray system was a success. The spray gun is still in its early stages of development, but is considered by many scientists and researchers to be the solution of various predicaments that occur when applying graphene onto large-scale products. The most common problem that would transpire within the other methods is that the layer would be uneven and coated by aggregations. The energy delivered by the supersonic spraying stretches the graphene evenly upon impact, and is the main reason for the spray system's lack of defects that are common within other graphene deposition methods. Reduced graphene oxide, an aqueous fluid supplied with low-quality graphene flakes, is inserted into the de Laval nozzle throat. These precursor molecules are then converted into fine particles during its exposure to supersonic speed gas stream. The reduced graphene oxide molecules, argos, are then transformed into tiny droplets in the air, subsequent to its deposition from the nozzle. These graphene droplets swiftly evaporate and evenly disperse, all while suspended in the air. Upon making impact on its substrate, the surface of the material, the graphene evenly stretches out and expands due to the high kinetic energy delivered by the de Laval nozzle. A single atom-thick layer of graphene is formed upon the substrate. Results from conducted experiments. Upon departing the spray gun, the graphene flake's tendency to aggregate is reduced due to its quick evaporation and dispersion, much to the researchers' surprise. This spray method produces flakes that contain substantially less defects that would commonly occur. Common graphene defects including holes and lumps in the layer, and the stone whale's defect were absent upon surface impact. The large amount of kinetic energy delivered by the supersonic nozzle creates the healing of these defects. As the graphene flakes stretches upon impact, the carbon atoms within the graphene rearrange to create seamlessly perfect hexagonal lattice structures. The result of these perfect hexagon structures is the creation of a smooth, even layer of graphene. This is a large contrast to the applications of graphene onto large-scale substrates prior to the creation of the graphene spray gun. The graphene layers would commonly contain defecting clumps and spaces, which troubled scientists ever since the discovery of graphene. The graphene spray gun is also regarded as inexpensive when compared to the other methods of large-scale graphene applications. One main factor for its inexpensiveness is that the graphene layers require no post-processing treatment, which was common in the other methods. The other factor is that the spray gun is remarkably simple in both its production and utilization. Usage, due to graphene's distinctive properties, such as its high strength, high electron mobility, mechanical stiffness, and its remarkably well ability to conduct both electricity and heat. It serves a plethora of applications, serving primarily in the field of electronics. Several graphene applications include its usage within flexible touch screens, integrated circuits, reinforcement of electrical properties to plastics, biological engineering, optical electronics, energy storage, and photovoltaic cells. Graphene may also be utilized in the field of composite materials and nanotechnology. With the implementation of a graphene spray gun, the material may be evenly dispersed upon a large-scale substrate. The graphene spray gun also provides a more efficient and effective utilization of graphene due to its lack of defects that would otherwise be found in different dispersion methods.